we can.
Okay. Thank you, dear Chair, for the introduction. So my presentation, I will jump directly to the outline of my presentation. I will start with the motivation and background. Then I will present different tunable filters and tuning techniques based on TM mode dielectric resonators. Then I will end my speech with the conclusion. As we know, the current development in multi-standard multi-communication systems have urged the need for more compact and more efficient and easily reconfigurable microwave filters. When it comes to tunable filters, we are dealing with two things. We are dealing with the structure and we are dealing with the tuning mean. So when it comes to the structure, the electric resonator structures appear as a very good candidate for tunable filters application because it's compact structure, the good power performance, and also the high quality unloaded quality factors, and also the more feasibility when it comes to reconfigurable structures. So, and for that, many tunable dielectric filters were presented in the open literature. Those structures were presented based on TM mode resonators and hybrid resonators, and also using different tuning concepts and means, mechanical tuning mainly and electrical tuning, and both they can be combined in a switch rod tuning concept. Anyway, all of these designs suffer from various limitations, including the large circuit size, because we mainly need a room for obtaining the tuning mechanism and getting the tuning and let the tuning concepts operate, and also the increasing losses and also the limited tuning capabilities. So what we need a more compact structures and more efficient tuning concept. That's what we will propose and what we will suggest in our next projects. The first one is a microfluidic-based ultra-wide tuning technique for TM010 mode dielectric resonators and filters. Okay, for the concept and the design, we propose TM010 mode dielectric resonators. Why? Because it has various advantages in comparison with the other dielectric resonators, including the substantial volume saving, the better spurious performance, the mechanical stability, and for us, for tunable filters application, is the more feasibility for tuning. What does that mean? If we saw the distribution of the fields in the TM010 mode structures, we can see the E field is focused in the center of the resonator. That means we can just introduce a tuning element here in the center to achieve tuning with good capabilities. The mechanism that we are using here for tuning is we use liquid metals because it has different advantages, including the low loss, the compatibility with high power, and the low cost also. So let me show you the concept and the configuration of our structure. It is easily based on just the actuation of the liquid metal inside the hollow dielectric TM010 mode structure. As you can see here, when the liquid metal actuates inside the channel of the resonator, it cuts E fields, then then the frequency can be tuned. So why we propose this configuration? Because TM010 mode dielectric resonator is ideally suitable for the liquid metal proposed mechanism. We don't need much, let's say, setup needings. Just we need to bring a pneumatic pump and the liquid metal in a container, and then we just pass it through our dielectric resonator. In comparison with the conventional, let's say, screw-based tuning, here we are sure that we have a very good contact because the liquid metal will be in direct contact with the cavity. The other advantage here, that this mechanism, I can say, gives us the most possibly achievable tuning range. Why? Because the liquid metal will be in direct contact with the ceramic. That means there is no gap between the tuning mean and the resonator. That means we cut the highest possible electric field in the channel. That means we can get the highest possible achievable tuning range. That cannot be possibly achieved with the conventional tuning means because we need a gap between the, let's say, if we were using a screw, we need a gap between the screw and the ceramic. We don't want to cause any break. Let me show you results to prove our claims. Here you can see the tuning range is more than almost 120% tuning capability. Also, there's interesting advantage here of interesting switch off without the need for any RF switches in our circuit. The concept can be applied in higher order structures. This is second order structure, as you can see, also the wide tuning range. Here's a comparison between in a single resonator structure with other technologies and other tuning concepts, basically using liquid metals. Okay, as you can see here, our proposed configuration has the highest initial Q factor and also have the widest tuning range. And also you can see here the intrinsic switch of feature. And in addition to all of these, as I mentioned, this configuration is, let's say, easy to be realized and easy to be applied, not like the other configurations. But someone might say, yeah, this might be interesting regarding the wide tuning range, but I'm not sure when it comes to deal with the liquid metal thing. I'm not sure also with the high degradation Q factor here. That's what we tried to suggest in the second project here, is to introduce a more, let's say, realizable design concept, which is we call it the rent cap tuning technique for TM mode electric resonators and filters. As a background, we still want to stick with the TM01, not TM01, but TM mode structures, because we want to benefit from its advantages. But when it comes to the, let's say, the tuning techniques can be applied here, we are just limited by the tuning screws, which are not favorable for us because the increasing losses and also the limited tuning capabilities, and also the appearance of unwanted, let's say, effects at high power levels like multifactor and corona. So what we propose is just bring your TM mode structure, eliminate your screw, and try to use this surrounding cavity in a proper and wise way. We introduced a hollow cylindrical envelope as a tuning component. We called it a movable hollow hollow cylindrical element. We call it a re-entrant cap. Okay, here the tuning is the frequency tuning is achieved by two means simultaneously using this single cap tuner. How is that? When we move the tuning, the cap tuning inside the resonator, the part of the cap outside the cavity will work as a movable side wall. This is the first one. The second one, the part of the cap that moves inside the cavity here will cut the fields around the resonator and also cause tuning. So for that, I call it double tuning. That means we will get wider tuning window, and also we can get higher Q factor when you compare it with the conventional TM010 mode structure, because we have wider gap between the resonator and the movable cavity. Additionally, we can use a feature by introducing a screw from the other side, which we can call it dual tuning. This will expand our tuning window. Let's see whether these claims are correct or not. We just brought two examples, one with just tuning screw and one with a cap tuning. If we look to the comparisons here, we have wider tuning capabilities when we use a cap tuners, and also higher average Q factors. Also, we use the dual tuning concept to extend our tuning range. Also, another advantage here we can claim is the higher power levels. Why? Because if you look to the, as I showed earlier, most of the E field is in TM mode structures is focused in the fundamental mode, is focused in the center. That means here the breakdown may happen very, very close. But when we look here, the field distributed per unit area is less than this one. That means the possibility of the breakdown in the cap tuning concept is less than, that means the power performance should be better. Let me show you some examples here. Second order structure can be realized easily with a wide tuning with a constant bandwidth response. Third order example also. This is simple measured results of a single resonator. So you can see the wide tuning of the cap tuning concept, the better Q factor when it compared with the screw-based tuning conventional technique. Okay, for those projects, the previous two projects are based on single mode TM mode structures. In the third project here, we said it is better to use dual mode resonators. Why we use dual mode resonators? Not just for giving us at least 50% size reduction in size, which is interesting also and good and attractive for applications, but also we can, at the same time, it means we will use half count of tuning elements. So let me show you firstly a background of this. Normally, or in the tree shade, you can find dual mode filters based on TM mode resonators, and dual band filters also based on TM mode resonators. You can find them in transversal configuration like this, but when it comes to tunable filters applications, transversal configuration are not the best ones, because the access for the resonators is very difficult. So the first thing we should deal with, and we should let's say design, is the dual mode filters and dual band filters in planar configuration. Then we can go and design our tunable structures. So let me show you the first one here. Is already configurable dual mode dielectric filters using piezo motors as a mechanism for tuning, for automated tuning. The concept is very simple here. We use the two degenerate modes, TM120 and TM210 modes as the dual mode structures. We in just a single resonator structure. Here are in planar structure. We use T1 and T2 for tuning. T1 for tuning the resonant frequency, and T2 for tuning the bandwidth. And I should mention here that if you look to the field distribution here, this is the HE field. This is opposite to the TM010 mode. This means when we insert the tuning element here, the frequency will not shift down, the frequency will shift up. Okay, let me show you here's the coupling topology. Here's the response of the filter. As you can see, this is a second order filter. We have two transmissions zero generated. The first one caused by the doublet configuration. The higher one is caused by the source to load coupling path caused by the first mode, the fundamental mode, TM110 mode. Let me show you some tuning responses. Here's the frequency tuning response. We got a frequency tuning with a tuning window of 15%. Here's the bandwidth tuning more than 100%. Here's the transmission zeros reconfiguration capabilities. Here we tune the lower transmission zero from the left side to the upper side. Why is the first transmission zero is why is the higher transmission zero is fixed? Here we use the higher transmission zero from left side to right side by changing the sign of the source to load coupling caused by the non-resonating mode. Here's some experimental results. As you can see, we got this similar tuning range, and interestingly, we got a volume saving when compared with the conventional structure. The conventional waveguide structures is very compact. We got a volume saving of almost higher than 70%. The second project now is the miniaturized dual band filters based on our dual mode structures, and we are investigating its reconfiguration capabilities. The first thing, as I mentioned, we need to design a planar configuration for our filter. The concept is similar like the doublet configuration, but here what we will do, we will move one of the modes away from the other one to get a dual band response. Here, like this, in this example, we just changed the corresponding dimension of one of the modes and shifted it away. The corresponding coupling matrix, as can be seen here, we can generate two asymmetrical transmission zeros as I showed by the non-resonating mode. Here's the second order configuration of this structure. Okay, it is just a dual. Each of the modes make a band, and we also have the non-resonating mode to create a source to load coupling path. Okay, the structure is realized in planar configuration. The coupling is realized by the feeding pins in angular configuration to feed to excite both modes at the same time. The interregional coupling is realized by inductive analysis with the central inductive post. Okay, for the response, you can see here's the response of our filter. We got an interband transmission zero to improve the isolation. This caused by causing a phase reversal between the two orthogonal modes. This physically obtained by the proper positioning of the output feeding. We also got two asymmetrical transmission zeros, as I mentioned, by the non-resonating mode. The important thing for us here check the tunability of this configuration. So we introduce this T1 screw. This T1 will tune both modes at the same time. Then we introduce T5, T6. This is for tuning the bandwidth. Also, we try to see whether we can tune each band independently. So we introduce T3, T4 to tune the first pass band, which corresponds to TM210 mode. Sorry, not TM120 mode, and no, 2M210 mode, and T2 here to try to just reconfigure the higher mode, TM120 mode. So let me show you some results. Here's the fabricated prototype. As you can see, it's very compact when it comes to dual mode structures. Here's the reconfiguration capabilities for both pass bands. Here, when we try to just reconfigure the first pass band, while the second pass band is kept fixed. Here, when we reconfigure the second pass band and the first pass band is kept fixed. The conclusion to my talk, I've introduced various tunable component tuning techniques based on TM mode dielectric resonators to benefit from its advantages. The presented designs showed different interesting advantages for applications, including the compact size, the wide tuning capability, simple configuration, and the high quality factors. But one thing, if you notice in those designs, there's let's say a clear deterioration in the Q factor. This we recently dealt with in recent research. I hope it will be available to the scientific community soon. If you can see here, the frequency is tuned, while the Q factor is almost in a straight line. This is very great for tunable filters applications. So that is the end of my presentation, and thank you and welcome for any questions.
Okay, thank you for that.